Here we go again. So what's the most confusing things going on so far this semester? That's a tough question. It's all very confusing. I finished grading the homework. It took me forever. Oh, and I forgot my pencils. All right, well, this is gonna. It's already been recorded. Talk amongst yourself. Forever. The doctor, this jerk asked me yesterday what classroom I wanted to teach next semester. And he says, you can get one over in the Hersey Center. I'm like, oh, that'd be cool. And then now I'm thinking, you know how many times I forget something and I go back to my office? It'd be like no pain. Yeah. I'm going to teach you the class called Mechanisms, which the subtitle is Doohickeys, Gizmos, and Gadgets. It's just like trying to make mechanical things that make a particular motion that you want. And I have all kinds of like things to carry over to that room, and I'm not looking forward to it. But still, it's brand new. I like brand new things. All right, so what would you guys have to carry? Do you have any requests?
Maybe a curved beam.
A curved beam? Okay. I wonder if there's one in this book. A curved beam. A 3D Moore circle. I like that. Okay. I wonder if they have any curved beams in Beard Johnston. See if, look up C. I have curvature. Nope. Probably not. All right, so we got requests, and we could do we could do a pressure vessel too if you want to, or we could try it. That might be a lot to do in one. Okay.
So like it's open textbook, but can we put like sticky notes on like certain pages?
Yes, but not with lots of long things of writing.
Yeah, just like this is exactly what I'm doing.
That's fine. Yeah, just I encourage you. It makes sense to do. I encourage you to keep your textbook forever as opposed to selling it back. But I understand it's expensive, especially if you bought the full version of the thing. It's like $280 or something. That's crazy. Textbook companies just trying to barely hang on. Okay, well, we have one of this guy. We could attempt this one or that one in terms of curved beams. What do you got? You got any preference?
Can you move down a little bit on that to the very bottom example?
There you go.
Oh, that's good.
Yeah, that's a tough one. Way to pick the tough one, man. Because I think they actually want us from the table, the integral can be evaluated for the rectangle and a circle by a value in A over Rn. Yeah, so this one requires a whole lot of more effort because that's not one of our standard sections.
I guess 145, sorry.
145, okay, let's see if there's anything quirky about this one. It's got a big old radii right there. I'm assuming this is a square cross-section. The cross-section at the critical location is elliptical. Oh, you bastards. With a major axis, all right? So you can picture what that looks like, right? It's got a kind of elliptical, I think, with a major axis of 3 inches and a minor axis. So I think they're saying like that is 3 inches. And this is 1.5. I'm assuming it's that it's where that I'm right here. I'm looking at it from that direction. It kind of makes sense, but maybe I don't know. let's see if we could say the load is 20 kips with the geometry as shown in the figure. The cross section of the critical is elliptical with the major axis of 3 inches. They don't really say, right? Because it just easily have been like that right there, right? I like writing in books because I could get in trouble for it when you're in grade school. You can get all kinds of yelled at for writing in your book, and now I own a book, so I'm just going to write the hell into. I will write it. Go crazy. Okay, so here, write out our problem. There's something about a clipboard I like, and by a marine engineer, you know, we always drove. I'd go on board ships and do inspections and stuff. I always carry a clipboard like around. They had these metal ones. That was a terrible idea because you set it down someplace on something that's hot, and then you go to pick it up. Yeah, so I threw away all the metal ones that I had. I only had to do that once. Put it like on a superheated steam valve. Like, oh, I just put that right there. Oh, no, yeah. It's like part of my hand came away from it. All right, so this is problem 3-145. The reason why I pointed it out is I just looked at the old school clipboard with it, and this just reminds me things going by. Yeah, and it's made out of this kind of wood. That's like, not really wood. Here's the problem. Looks something like this. Kind of like that. Should use my straight edge. Oh, no, it's curved, dude. I guess the curvature is kind of constant right there, yeah. Something more like that. So somewhere up here, and they gave us the inside radius as 12 inches. And it's aligned with, this is going to be 9 inches to there. And as they told us, I'm going to go ahead and assume it's this way right here. Let's see if they have the answer in the back of the book. This is very satisfying when you can get it. It's a little very discouraging. Let's see if they have 3-145 in the back of the book. Where'd about that thing go? There you go. Almost made it. 3-145. Darn, we don't have it. Oh. Well, I could look it up later. We'll look it up and see if we get the right answer. But testing yourself that way was the secret of my success as a student. When I started having the guts to just pick out any random problem and start trying it. And okay, and they said that the force is 20 kips. I hate kips. I must have known somebody named Kip once in my life and just didn't. I just hated the guy. Sounds like somebody that's like in one of those 80s teen movies where he was like, you know, he was the rich kid and all the valley kids are trying to make their way and they're going to close, you know, I don't know, something like that. All right, just stop talking. And we just want to find the inner and outer stresses, right? So it's going to be like right there and right there. So there's a lot of geometry to start with this, but in the wrong book, that would help. We want to go to that table, which I believe is table 3-4. There you go, jump right to it. And it's an ellipse. Are you kidding me? It's not in there. They don't have an ellipse in there. Way to go pick the wrong problem. It's all right. It's fine. You picked the wrong problem. So I don't know, do I really want to try to do the integral of this thing? I don't think so. I'm me integrating in front of you. I don't know if that's something that we want to do. But this is the main thing that we would do. First off, we could get the centroid of the thing. That wouldn't be impossible to do, but it's this integral that we want to do. I really don't want to do it. No? No, anybody? All right, we're going to do a different problem? Yeah. Well, okay, we're all agreed. Or we could treat it like it's a circle. Circle gets the square. Would have been nice. So much disappointment. I should be able to integral. You know, you think, you know, a PhD means that you could do all this stuff that, yeah. You think you'd think so? I don't want to start. One point I could do all this stuff, and if I went back to my office and I spent like an hour on it, I'd like relearn how to do it. So I don't just keep information like available all the time for access. It's just like, I learned it once, I could learn it again. All right, so let's pick a different problem. No shame in that, I suppose.
Don't ask me.
Okay, don't ask you to decide. I'm sorry about that, but it's maybe I should pick one from an old homework problem. Maybe I can. All right, let's see. Although I did make some of these homework problems are pretty bad. They're pretty long. Let me come back to the curved beam problem, and let's go for a 3D Moore circle because it's low-hanging fruit. We know we can do it. And we can just pick out random numbers. Actually, there's problems in the book where they have the 3D Moore circle type of things. So let's see if we could find whereabouts that is. Sometimes they'll be in order. Right here. It did not start. This whole session doesn't start off very well, did it? Let's see. Do we pick anything in this area that's 3D Moore circle? I don't know. I'll just pick out one of these things. We'll go for 50, negative 20. Oh yeah, this is actually a tricky one. They tried to trick. You can see it here. I don't know if you can see that. It's got sigma x, sigma z, and then tau xy. Oh, you tricky bastards, you. So this would actually be a 3D Moore circle right here. You can see this as the 3 circle diagrams right there. So let's go with the tricky one. So they said this is problem 318D. And they said sigma x is going to be equal to 10 KSI, because I don't do K at PSI. I don't like it. I was just looking at, no, it was 50. I'm sorry, I was looking at the wrong problem. This is the problem I wanted to do. 318D is 50 megapascals. And we had sigma z is negative 20 megapascals, aka compression. And tau xy was 30 megapascals clockwise. So let's just think about what that would look like in on a cube. Let's see. Let's say that we have a cube that's arranged this way right here. And we'll say that's x, this is y, and that's z, like we normally would. So x is tension. That's 50. Z is compression. So we'll put it over here, 20. And tau xy, okay, so that's going to be, if you're looking, you know, any time that you have that xy, that means it's in the xy plane. And it's, did they say clockwise or counterclockwise? They said clockwise. So clockwise will be this way on that face. Of course, it's this way on that face. And this is the 30 megapascals. And you go, okay, so how do I approach this? Well, remember the whole mission that we're on when we're doing a 3D Moore circle, is that just our mission when we're trying to find principal stresses is to get rid of the shear, right? So in this plane right here, which is the XY plane, right? That's the one that we're looking at from this angle right over here with creepy eye. This is the one where we need to get rid of the shear. And this is the 30. So we do that one first as our primary Moore circle. And we note that it's uniaxial stress in that plane. And I don't think I brought, no, I did. But this is a terrible one, so I don't know. I don't know if that counts. So I can go 50 here. Let's go 50. We'll go 10, 20, 30, 40, 50. 10, 20, 30, kind of like that. Better to use graph paper, but whatever. So on this face, I want to plot this face first. We have 50, and we have 30 going clockwise, which is the upper part right here, right? So here's our 30. Here's our 1, 2, 3, 4, 5. Here's our 50. I probably should have shifted this down some. And then over on this face, we have 0 and we have 30, right? So it ends up being right there. So I can, where'd you go, man? There you go, magical ruler. And boom. And let's see how bad of a job I did. It's actually not that bad. Well, now it's going to be bad. You jinxed it by saying that. Okay. Here you go. Here's your primary Moore circle. The C for this, C, is going to be 50 over 2. We could do that, 25. Our R, this is a pretty easy one. That's a good place to choose our R. We could choose this one, but this is going to be the simplest, quickest one. All we have to do is take that leg, which is actually C, and then we take this leg, which is that 30 squared, and what we're left with 25 squared 30 squared plus square root. And I think I get 39.05. So I could go ahead and predict that's going to be sigma 1. So sigma 1 is equal to, I don't know why I just made that plus sign, is equal to C plus R, 25 plus 39.05. So sigma 1 is 64.05 megapascals in tension. Everybody following what I've done? Just going through the routine. The next one is going to be over here somewhere. And that's going to, and sometimes I'll call it A and B when I don't know yet, right? This one I can predict, though, is going to be sigma 2. I can predict that because I'm already going to say, well, what's the other? We haven't used that 20 yet, right? But we have twisted this thing we've kind of like twisted it like this way right there, right? So because we kind of rotated this thing down the cube, and I didn't emphasize this, but any movement that you make here for an angle, right? You can almost think of that we're taking that point and moving it down, just like we're taking this point and moving it up. We've actually rotated that square. Any movement that you make here, it's 1/2 the angle movement over here, right? So like, or I should say, if I rotate it here, this is twice the angle of the rotation. And one way that you could even think of that is like we had this face, this dot represented this face, and this dot represented that face. So they're actually 90 degrees apart, but here they're 180 degrees apart. So as we rotate them, so there's, all right, this is 2 theta or whatever we decided to make the thing, and then this thing rotates theta. But I don't really emphasize that because the main point is that we're getting rid of this. But anyway, C minus R, that's going to be 25 minus 39.05. So we get like 14.05 negative, but I'll go right ahead and just write it as compression there. I don't have to put the negative in there, so I cheated. And now what we're left with is this guy right here. But if you took a look at what we've just done, like, and maybe if I could even just like try to attempt to make this kind of thing look right here. What we've really done is we've kind of like taken this cube. I'm not feeling it right now. And we've kind of rotated it like that right there. So that, and I meant to try to make this axis look the same, right? That 20 megapascals is still going on that face, but now we have on this face, it was 50, but now it's going to be 64.05 megapascals. And this face right here is now 14.5 megapascals. Does that make sense what we did? So now when we go and we take a look at maybe this face right here, like maybe we're going to look down this axis where my pencil's pointing, and all we would end up seeing then is going to be the 20 megapascals that are right here, and we'll see the 14.05 megapascals that are now on this face, because the 64 is coming out at us, so we can't see it. So if we were going to draw this Mohr circle for this one right here, it doesn't have any shear in it, so it's already going to have some point. So it's going to have a point like right there. And I didn't make my scale very good, but that right there is sigma 2, so that really is supposed to be 14 point here, but it actually kind of ended up looking more like 10. But it's because I made the hash marks myself, right? And I'm not accurate in how I'm thinking. So that Mohr circle looks like that right there, right? One of these points represents this face, and the other one represents this face. And now we could do the same thing. We could look downwards this way, looking down at the axis, and we would have now this way. I got my 20 megapascals, and I got my 64.05 megapascals. I think I did that right. Yeah, I'm looking down this way. So when we plot, it's going to be this point for that 20 face and this point for that 64 face. So their overall one, if I got brave, because this is a very finicky compass, but it's going to be pretty good. There you go. That wasn't too bad. There's my 3 more circles. Now there's one of them is not 0, right? Because just the arrangement that we have right here. Quite often one will be 0 if you have plane stress. But this is not plane stress because we have multiple things going on. And then, but the most important one out of this, and I did a bad job of scrunching things in here, is the tau abs max. I mean, you could argue it's the most important. And, I should also say, I didn't write it down, that the sigma 3 is 20 megapascals. Wait, can't write that. It's not too far down. There you go. 20 megapascals compression. So now when we go to do the tau abs max, that's going to be sigma 3 minus sigma 1 divided by 2, or 64.05 minus, whoops, I flipped them. Crazy, thank you. I made a video last night for a dynamics homework problem and got myself all confused. So I have Camtasia, which is a kind of a video editing, but you could also do screen capture things. It's really nice, actually. I bought it myself. and I'm splicing it apart. I'm trying to cut little chunks of it out and throw it, and then put little annotations like, no, dummy, that's a negative. I'm like we're writing my own little thing here. So let's say 64.05, and we're going to add 22 divided. So we end up with 42.03 megapascals. So that's probably going to be the main answer that we have. Other answers we might have are these right there, right? So the three principal stresses are these. And I'm doing something I ask you not to do, right? Which is to box things. I like it when people rewrite the thing at the end. Theoretically, I could just go to the end and go, check, you're good to go. You would think I could do that. But most of the time I go like hunting, like, hey, you know, towards the end of the semester, I'm just going to start phoning it in. Just, you know, it's not true. But sometimes I was going to start doing a grading method where I do like, I'm going to call it the holistic grading method. Like, I look at the whole thing, I'm just going to mark little X's by things that are around and go, you appear to be 85% successful. Where'd you get that? Where did you get that number from? Come out of here. Because trying to add this stuff, it's only that students tend to and actually it's a good sign because you know that they're not cheating, they're not copying off other people. If everybody has a different answer, everybody made a different mistake, and a mistake unique, completely different for them. It's an exciting thing. Okay, what else besides a curved beam right now? We could go. I might go steal a notebook and see if I have a good curve. I'm afraid to like create one myself, but I could just invent a curved beam problem. Pressure vessel is a very important thing, and we don't have enough in this book, I think, personally. I do think that you know, I put the hints. Anybody tried the homework? No pressure. It could be rhetorical if you'd like. I mean, why would you do it? Why would you already have done it if it's not due, right? But I did that strain gauge one. Is tough. It is a tough problem. I was almost on the verge of like going, nah, let's get simplify it. But then I'm like, no, you can handle it. I just don't want to overwhelm, but I also do want to like challenge, you know, and kind of keep pushing forward. But the people who haven't been doing successful yet on the problems, this might be too much. So I'm a little nervous about it on your behalf, but I hope people don't just give up and they actually come to me instead and ask for like guidance, because I also did put the little hints in the back. And that's a pressure vessel problem. So let's say I had one that I invented one time that I thought was pretty clever. Right, so I had this, let's say I had some maniac created a heat exchanger, or has a heat exchanger, and they got like little legs that look kind of like this right here, with little holes that bolt it down, right? So maybe if you look at the front view of the thing, here's where it bolts down, right? And for whatever reason, somebody made a foundation so that one end of it looked like this. Like say that's one end of it, and the other end of the foundation was made like that. Right? So, and then somebody just got bolts and they just cranked and made that thing so that it fit, right? So it's putting a torque onto this, right? But also, these are of the sort, right? So there's like a twist that's taking place into this thing, right? And we will come up with, let's say that this thing is 36 inches long. Let's say that this diameter right here, the outside diameter, I don't know, that looks like it could be 8 inches in diameter. And let's pick a wall thickness. Let's make it really small. So let's see, 4 times 0.1. Yeah. Let's make it the thickness of the thing is 0.4 inches thick. Right. Then it'll be. Then I think it'll be 0.1. Right. Is the ratio. So we could use the thin-walled stuff. I also said that the stuff inside this is relatively heavy. So let's say that it's, let's say the whole thing weighs, I don't know what it's full of. Let's say that it weighs 800 pounds. So everything inside is 800 pounds inside this thing. And let's see what else we do this, that the pressure, let's put a little pressure gauge onto the thing. Let's say that this is got a pressure of, oh, I don't know, this is crazy, 1,200 pounds, PSI. These could be just crazy numbers, right, that I'm picking out right here. Okay, so the things that are taking place here, for one thing, this is a distributed load, that 800 pounds. So let's take a look at the thing at like a beam. And at least it's symmetric, but we could take that and treat it like this right here, right? You're okay with this? That's the kind of beam. And if it's 800 and what did I say, 36 inches, so that's 800 divided by 36. So it's got 22.22 pounds per inch is the loading. And here's our reaction. We'll call this A and B over here. So here's Ray and here's Ribby. And we shouldn't do this, but we know that they're both 400 pounds. We shouldn't write the sum of the forces, but we did. Because we know it's symmetrical and they got to be 400 pounds. The whole thing's 800 pounds. But here we have a little bit of a difference that we don't usually have, is we're going to come up 400 and then come down 400, right? Remember how that distributed load thing worked? I was just trying to make things a little bit more interesting. So there's a 400 come there, and here's 400 coming right there. And so that's going to mean that this is going to be like this. And we're going to, the moment diagram of the shear moment diagram is here. And this should be 400 times, and this is 36 inches long, so this should be 18 inches. So 400 times 18, 18, and then divide by 2 because it's a triangle. So we have a moment of 3,600 inch-pounds. So we can predict that that's going to be where the maximum stress is going to be in the center of the thing, which kind of makes sense for the layout of the thing. So let's get some, oh yeah, and oh, by the way, this thing was bolted down when it was cold. But somebody has made, this thing's full of steam. I don't know the exact temperature of steam at 1200, but let's say that it's 800 degrees Fahrenheit. Okay, so we've made ourselves a complicated little problem right here. I'm going to get some geometry out of this. So go pi over 4, and if the OD is 8 inches and the thickness is 0.4, then the ID of this thing is going to be 8 minus 2 times 0.4, or 8 minus 0.8, or 7.2 inches. Did I do that right? Okay, you're just going to agree with anything I said, right? That's good. Yeah. By the way, that's a good for your significant other. Just go ahead and just agree with everything. Just nod and smile. That's my policy. It's not true. I'm a big old liar. 7.2 squared minus. Got to keep watching the time though, but I think we'll be able to do it. Don't want to go to the hyperspeed mode, but we can do this. Someone might want to be checking my math because I don't really trust my math. I just said that it was 9.550 inches squared, and the I is pi over 64, and that's going to be D. Well, it's going to 8. Let's just put the numbers in. 8 to the 4 minus 7.2 to the raised to the 4, and so 8, 4. I like my other calculator, but let's see. And then 7.2 raised to 4, boom. Subtract them out. Multiply by pi, divide by 64. And we get a 69.15. I'm not confident I put that in right, but we'll just go with it. 2 times that is 138.3 inches fourth. Okay, I think I could go for. Let me do I checked already, but let me do the other thing. We know that the radius is equal to 4 inches, and the thickness is equal to 0.4 inches. So thickness over radius is 0.1, therefore thin. And we can start getting stresses. Now, for one thing, the stress that we're going to be looking at, we're going to say that bending is going to be something that's really going to dominate most everybody else. So that bending is going to happen at the top and the bottom of this. We're okay with that? So we also will have axial stress. Why is there axial stress? Well, that was true. The pressure will, but we'll also have axial stress because it wants to expand, but it can't. And we're going to make the gross assumption. We treat it as like simply support right here, but it will also say it's not only simply support, but it won't allow any axial expansion. So I didn't really cover this, but one of the things that we should be doing as we go along here, as you know, throughout the course and throughout all of your courses, is you're learning to learn so that you can, not just learning stuff, but you're learning so that you can, if a new situation comes up, you can start figuring it out from stuff that's in the textbook. So first off, we could say that this thing is made out of steel, carbon steel. So we have this lovely thing here, the coefficient of thermal expansion is 6e to the minus 6. And how do we use that? Well, probably instead of using the canned formulas right there, we could just go ahead and use this, right? The stress is equal to that coefficient of expansion times the change in temperature times the elastic modulus. Does that make sense, though?
That's the stress for expansion.
That's the stress. It is in the condition in which it's constrained, it would expand except you've constrained it. So now that turns into compression because it wanted to get longer and you didn't let it. So we'll go this is going to be the axial stress, we'll say, is going to be alpha delta T E. So we'll assume that it was built when it was at 60 degrees. So we had a thermal expansion of 6e to the minus 6. So that delta T would be 720, and the elastic modulus is 30e to the 6 for steel. Close enough. Some steels might be slightly different.
720 or 740?
740 because math is hard.
I agree with that.
There's too many numbers. Beavis and Butthead. You ever see Beavis and Butthead? You know what I'm talking about?
I know what you're talking about.
It was a great TV cartoon, right? Yeah. Yeah, the movie wasn't all that great, but I liked it because it was actually one of the things I do admire on that is Mike Judge was the name of the guy that wrote it. He was a former engineer and decided to become a cartoonist. Right? So, all right, so I've really made this too ambitious here. It was 133.2 KSI. So in compression. So we have to be on the lookout for that. But we're going to have compression and tension in our heat exchanger due to bending. So check that out. So we'll have the bend is going to be MC over I, and we're going to have that 3,600. The C is going to be 4. We're going to go to an outside fiber. Let's just stick with an outside fiber in this one. and 69.15. So this is probably not going to even be close to the amount compared to the thermal expansion. But it's just for demonstration. So yeah, we barely get anything. 3,600 times 4 divided by 69.15 is only 208.2 psi. It's both tension and compression depending on which side you talk about. Like it'll be compression on the bottom and it'll be tension on the top. Because you can picture the thing sagging, right? Did I say tension on the bottom? Should be tension on the bottom. I should have said tension on the bottom, compression on the top. So far we might want to add the compression in there. But let's also take a look at well, here's the hoop to start with. We know that it's the pressure times the inside diameter divided by 2T. So the pressure was 1,200 psi. The inside diameter, we recorded that somewhere, right? Yeah, 7.2. And by the way, this is not DI plus T. It would be if we were dealing with the inside surface. And maybe we would want to, I don't know. We could have checked that, but we're not this time. So I got 1,200 times a 7.2 divided by 2 divided by 0.4. So we get a respectable 10,800 psi in tension. And then we know that the longitudinal is just going to be 1/2 that, but we could write it again anyway. P di for T. Two divided 5,400. I don't know why I switched over to. I just didn't want to write down. Okay, that's why. PSI, and that is tension. Okay, so because of the nature of the loading, transverse, we wouldn't have any transverse shear. You go, why? Because like looking back over here, that force, the load, which is all about the beam. For one thing, actually, here's another reason why. Because we would get that transverse shear from this spot right here. Because we're going to take it from the middle. We've already kind of decided that's where the worst spot is going to be because of the bending. But you'll notice there's no transverse shear. But it also would be no transverse shear because if there were transverse shear, it would be the maximum would be on the sides to each side. But we're looking at a point on the top or the bottom. The last shear, though, is going to happen, is going to be the torsional. TR over J. But how do we go about doing that? Well, have we ever looked up and seen TL over JG? You ever seen that? Yeah, this is the angle of twist that we would have, right? Let's say that this maniac this is only 2 degrees off. I'm just picking 2 degrees, right? So we'll say that this thing is equal to, and that's got to be in radians, by the way. So we have to divide by 180 and multiply by pi. So that's 3.491 e minus 2 radians. I need G. I can look it up, or I could try to rely on what my memory is of the modulus of rigidity. Isn't that a great name? The modulus of rigidity. I do believe it's like 11. Let's see if Shigley gave it to us, or we have to calculate it. Because we just used it the other day for strain gauges, right?
Like 27.
Yeah, for let's see, carbon steel, it should be 11.5 according to them. So G is equal to 11.5 E6 psi. So We have T, that's a torque. So this is going to be the torque. I don't know, did I get that? Can't see. This T is going to be the resulting torque. It's 36 inches long. It's got a J of 138.3. The G we just found out 11.5 E6, and that's going to equal 3.491 E minus 2. So we get a torque. It might be a huge number, by the way. So we're going to 11.5 E to the 6 times that. Oh yeah, I think we're going big. 138.3 times it divided by 36. Woo! We got a large torque. 1.5421 E to the 6 inch pounds. That's huge. So that's going to be a big stress. 1.5421. It's still got the radius to that outside fiber is 4, and we still have a 138.3. So 4 times that, and then 138.3 divided. Okay, so it wasn't as bad as I thought. 40. I'm switching back to KSI. I'm sorry, I'm jumping back and forth. KSI. All right, so now we got to decide where that stress element is going to be the worst. Well, we know that I got compression, so I think that compression and that compression are going to add together to make it the worst case. We're going to be alleviated a little bit by the longitudinal. Now, here's a big deal for us, right? So I'm telling you the answer, but now I want you to actually think about what's happening here. Let's take a look at a exaggerated cross section. All right, so we're looking at this thing right here, and let's look at this cube that's at the top, and let's take a look at the cube that's on the bottom. Right? All right, so for bending, we're going to have compression and tension. And I say that because, right, if it was sagging, the top would be compressing and the bottom would be stretched. You can see that there with the little ruler? That's true? Okay. There's going to be compression due to the thermal expansion. Maybe I shouldn't have called it axial up here. Maybe I should have called that therm. I like that better. So therm. And that's uniform across the whole thing. And what else we got? We got longitudinal. Wants to make it longer. Hoop wants to go this way right here. I should have wrote T. I wrote T up there, so I'll go T. And then the last one is going to be a twist, right? So if, let's say it was, this is the end that's like this, and this is the end that's like this, right? So what we've done is we've twisted, in order to get this down, we've twisted this way, so the whole thing is experiencing a torque that's kind of being placed on there in order to force this thing to close down. So that twist is going to be this direction on that face. So when looking at it right here, if, let's say, I guess I just flipped it this way, so there's the hoop right there. So I'm saying that it's going that way on that face. And the sum total of these is going to be a compression there. And the same thing true here, except that this is coming this way, so that's going to come that way on this guy down here at the bottom. I don't know why I just thought of that. So like looking at these, it appears to me that because we have compression from the bending and compression from the thermal, it's going to be slightly worse because the bending didn't really turn out to be a whole lot, only 208. We're probably not even going to know it. So if we were to try to, let's call this the coordinate system here. Let's call that X, Y, and Z. So we're looking down. Let's see if I'm going to crawl this thing the right way. I think I kind of messed up by having it rotated that over the way over there. But hoop is going to be in the Z direction. So this is going to look like this, XZ. Whoops, you can't see me. XZ, right? So sigma X is going to be the therm plus the longitudinal plus the bending. So that's going to be a negative 133.2 plus the longitudinal, which is going to be a positive 5.400. And the bending on the top surface is going to be 0.2082. I'm sorry. Get that out of the way. So I'm going to say I got a 133.2 and 5.4 and then 0.208. So I get a 128.0 PSI compression. And my sigma Z is 10.8, right? Because that's the hoop. 10.8 KSI. I said PSI up here, I meant KSI. Sorry. KSI. And this tension. And then the tau, and this is going to be XZ, is going to be, that's the 44.6 KSI.
Where's the hoop on the
This is the hoop right here. And right there. But we're gonna use a top one because that's gonna be where the worst compression is gonna be. So let's take a look at this. This is a strange situation because we have a really large compression compared to right. So up on here we'd have like 10.8 KSI, and this would be our 128 KSI, and then we just said that this is going to be 44.6 KSI. And because it's an outside surface, we don't have any radial, right? So we don't have anything that would be in the y direction. Had it been on there, right, we would have a radial in the y direction. We have a stress in the y direction. And if it was on the inside surface, oh, it's just going to equal the pressure, right? So we had 1200 PSI, so it would be 1.2 KSI in compression. So a quick more circle of this, and I think it really helps me to like write out one of these guys like here as I'm doing it. I guess I just made that wrong. I just flipped it. Let me keep it the same way I had it before. Here's the compression, tension, tension. With my 128 and 10.8 KSI and a 44.6 KSI. So let me lift this up a little bit. Some more space in here. So we plot this face first right here. This is going counterclockwise, so it's down here. This is compression. So let's go count by 20s, maybe something like that. I don't need to go that far over that side. So 20, 40, 60, 80, 100, 120. I say one. So this is 120 right there. This is 100. So then there's 140. And so 20, 40, 20, 40 right there. So we have something like there and something like that. So coming over to here, 128, there's 130, so there's 128. Graph paper would really help. That's one of the faces. That's this face right up here. Now we'll do this other face over here. So this is in tension. So it's something like this right here, like this 10.8. So this is 20 right there. So it's going to be something like right up in there. So C, and this does not look symmetric, so it's going to be all kinds of messed up because I didn't make my tick marks very well. But the average of these would be a negative 128.0 plus my 10.8 divided by 2. So I should get a negative 58.6. Obviously, it should have been like, yeah, I guess it was, this is 40, not terrible. And then the radius for the thing, this is hard to figure out, this radius, so I would pick this one right here to figure out. So the radius is going to be the square root of, and I'm going to take this value, 128.0, and subtract out the center, right? So that's 58.6 squared, and the other leg is just the 44.6. So 128, 58.6 minus square it, and then 44.6 squared plus square root. I get 82.50. So my sigma 1 is C plus R. So that's the 82.5 plus the negative there. So we're going to have a 23.90 KSI. Sorry about that. Let me look this up a little bit. And sigma 3 C minus R, which is going to be 58.6 and 82.5. So we had 141.1 KSI. And in terms of our big old Mohr circle, I'll fudge it.
Are they two negative? They're not going to,
Yeah, the compression, you're right. Sigma 3. I call this one Sigma 3, right?
oh,
Because I knew he was going to be there. I know the Sigma 2 has to be 0. So we would have a itty bitty more circle right there, right? And over here, this is Sigma 3. We would label this Sigma 1, Sigma 2. What's tau abs max is up at the top. And we could attempt to make the middle more circle. Like that. Tau abs max is Sigma 1 minus Sigma 3 divided by 2. Or so this, in this case, that's going to be 23 point. Actually, this is stupid because it's going to be in this case when this takes place. No, it's not true. It's not true. This is fine. Okay, minus 141.1 divided by 2. Did I do that correctly? I think so. Yeah, it should equal the radius. Yes, it does equal the radius. Okay, 82.5. KSI is the tau abs max. I figured I'd throw one at you that was like just crazy off the wall. Just everything. Kitchen sink, except now it's a heat exchanger. Yeah, I made that my first year here. I made it a homework problem.
nice.
I think I've had a lasting impact. Maybe not in a positive way. The students are like, oh, wow, that's a tough one. But this other one, this one I just gave you, is a tough one. It really is. But I'd say one of the most important engineering traits, the most important engineering trait, in my opinion, is to care. To care about the thing that you're working on. And then all the other ones kind of fall from that. But amongst them is like this perseverance, right? And diligence, and just like, just like, you got the thing, it's a pain, but you're just going to dive in and like get it done. And then like pay attention to all the details as you go along the way, and a tough problem can help you focus on doing that kind of thing, or it could just overwhelm you and make you want to become a business major. Which you all should be getting a minor in business anyway, starting your own company, that kind of thing. Because if you're an engineer and you're working for somebody else, you're never going to be rich. You want to make a lot of money? Start your own engineering company. All right, so there we go. Another one in the books. I'll try to figure out a curved beam problem. I don't know if that's going to help you at this point, because that's the homework. Make sure you're not shy about asking for help over the weekend. I will monitor, probably not during the Buffalo Bills game, because I won't be very helpful to you.
They're playing the Dolphins, right?
I think so. Yeah. Maybe next week would be better, because then maybe